back. And this week we're going to start talking about stars, since we've now equipped ourselves with both a little bit of a feeling for where they are on the sky, or in the night sky, and we've talked about how stars glow as black bodies, right? We talked about as things are hot, they glow. The hotter they are, the bluer they glow. And so we'll talk about the life of stars, and then next week we'll talk about the death of stars, and then we have the midterm. And since if I use the dreaded M word, that's when everybody starts to feel uncomfortable. So I will talk about the following things. One, I've been asked to flag anybody and that I worry about. And so I want to explain what worrying for me means here. It's when I see no in-class assignments at all, which means that you weren't here, which means I'm probably talking to the wrong crowd because you were all here. But if you were flagged for that, it's because you didn't have in the group work, so as far as I can tell, you weren't here. Or for example, that there were assignments at the beginning and then they suddenly stopped. That's a worrying thing for me. So if you're flagged, and I think I only have to flag about 3 people, and they're probably not here, but if you're being contacted by U of L, this is to, hey, do you need help? Is there a particular issue? Did your computer die and can you not get the pre-class assignments anymore, or stuff like that? Is there something technical we can help you with, or something else? If there is an issue, and you're running into this now, come let me know, because I do not like failing students on the fact that their computer died. That's not you, that's your computer. And so if that's an issue, let me know, we'll work something out. Okay, so that's the first thing, and I always feel like I need to be very clear about it, that we're being asked as professors to flag people that, oh, there might be a problem here, do it early so that we can intervene. And the second thing is, hey, do your assignments, because this is from previous years. Basically, the number of homework assignments people completed, and then their final grading percentage points. And I don't know if you can see this, but hey, we learned how to interpret certain graphs here. Bit of scatter, but yeah, there's definitely a trend. The more homework people do, the better grade they end up with. Same thing for the number of group works that they complete, so in-class assignments, more completed, better grade. And even if people overshoot the 70%, but as soon as you're at 70%, you've already got the full marks for that. Just keep going, I would say. Or the number of pre-class assignments, like if you do a bunch of pre-class assignments, your grade will improve. You can say like, well, these are all the same people. Yeah, all the same people did all the assignments. What can I say? Basically, keep at it, is what I'm getting out of these graphs. Keep at it, and you'll get there. You'll get there with a grade that you'd like to have. Are we on board with that? This is what you're taking away from the graphs as well? Okay, so this is now what you, why I do this pre-post class assignment, for example, and I have this kind of information and see how I do. That's why I'm putting this all in graphs and what have you. Okay. Well, that was the state of the class for a short minute, because I want to make sure that everybody gets through this class and ends up with a grade that they like. And hopefully I've told you now how to get there. Okay, so heat gets around, and this is the part where I start talking physics for a minute. So heat gets around, and heat gets around inside stars in the same way that it gets moved around in your house. So radiation, it radiates through light. Convection, basically draft, moves through a room, and conduction, that's the kind of thing where, the reason that metal feels cold and wood feels warm, it's not as good at conducting the heat from your hand away. Who's heard of all of these terms before? Who's heard of some of those? Okay, most of you have heard at least some of those terms. This is a way that you can get heat around your house. So for example, if you have a fireplace, it radiates towards you like, warm fire. Although, considering the last few days, you're probably going, cool AC, but ACs don't radiate, right? ACs do convection, they blow cool air around the place. And then conduction We really don't use that for heating or cooling that much, although you can have conduction in heating your floor, for example. So heated floor is often a conduction heat. So there are three different ways to get either cool or hot through your room. So that works the same way inside a star. If we have the core, that's where the heat is, right? That's where the heat is being produced. And then we have a radiative zone. Everything is so compacted that it can't move. So you can't have convection. So one of them drops out. So you can only use conduction and then radiation, like actually light passing through. So those are the only ways that we can get heat from the core to the outer layers. At some point in the outer layers, it becomes not dense, lower density, so it's easier to move around. Think like you go from water to air, it's easier to move around, right? So the convection, that's where the heat mostly gets transported by convection. So you have the core, nothing moves, that's where the fusion is happening, then a radiative zone, and then a convective zone, and then on the outside, you then have to get the heat out from the star altogether, and that's where it gets radiated away into space. So we're back to using radiation to get the heat away. Now, once the energy is produced here from fusion, we'll talk about fusion versus fission. So how do we actually fuel a star? That takes about 100,000 years in this life, in our sun, to get that energy to get to the surface. It takes a while to get to the surface. You have like a hot core, but it takes a while to move the energy all the way out to the surface and then radiate out into the universe. There's a little bit of other transport, and that's those prominences. Did anyone catch the two prominences that you could see during the total eclipse? You could best see them on a picture, but there was like two little red dots at the bottom. Anybody saw it? All your eyesight is way better than mine. I just thought like, is that a pink thing? And then it was gone. But there were these prominences. So occasionally, the sun and other stars will eject things. So there's also that's also how you can get rid of energy. So you can eject the outer layers, right? That's a drastic measure, because you're basically shedding the outer skin of the star, but it is possible. So, and you can see these sunspots, if you're outside, and I'm not sure if it's sunny at the moment, but if it's sunny, you can actually get the sun in the solar telescope, and you can see those sunspots that they have. They sort of link to those prominences, flares. Okay, so stars work the same way as the heating in your room, just at very different temperatures and densities. It's just the same physics altogether. Okay? All right, so we have radiation, similar to how you perceive the heat from a heat lamp. Conduction, the same way metal pan becomes hot too. Convection, the circulation of material from the core to the cooler surface. So we have all these three ways to get energy from the center out to the outer regions, but sometimes one of them shuts down, especially convection. If that one shuts down, you have to have the other two sort of take up the slack. And so it becomes harder to move energy out. It just takes longer. Okay, so we remember these two kinds of emission that we had. We had black bodies, the hotter it gets, the greener and then eventually blue. And then we had the electron transitions, and that was how we fingerprinted materials. Yes. It wasn't that long ago, but so if we go hotter, the peak goes to the left, it goes to shorter wavelengths. If the whole star is cooler, it moves to the right to longer wavelengths. That's why I made hot blue and cool red, which is the other way around from how every possible tap in the universe works. So sorry about that, but yes, stars, when they're hottest, they're blue. And so the bigger I make it, the more area is under the curve. Area under the curve, is that a term you've heard maybe? Some of your math majors and science majors may have come across that. Essentially how much area you can shade underneath here. If it's bigger, you just essentially end up with way more area to shade underneath. So that is both proportional to the radius, so size of the star, but also the temperature. Okay. Absorption and emission lines. Remember those? Little thing? You were here for the lamps. Yes, okay, for some emphatic nodding, right? So that's how we get the elements that are in. So a spectrum allows us to fingerprint each element. So that's how we get the elements that are in the star. We're looking at just a glowing gas cloud. We get these. It's dark except for the lines that are glowing. So that was what those tubes were. And so we end up with three kinds of spectra. Either you have a hot light source, so basically a ball of something hot, a star, with nothing around it, would essentially be this black body. Like you see this gentle curve, you see light at every frequency. So if you split the light up according to color with the prism, you end up with light anywhere. If it's just a cloud of hot gas, we get just those emission lines. But if we have a hot source with an atmosphere, like a corona, like a stars with an atmosphere, you get light almost everywhere except for the elements that are living in the atmosphere of that star. So we can see what the atmosphere of a star is made of, and that's how helium was discovered. But we'll see them as absorption lines against the spectrum of the black body. So for example, if we look at our sun, we see the sun, and then a little bit of light is removed by the corona by absorbing it and then radiating it in every which way. So then we see a background of light everywhere except for a couple of places where we see the elements in the corona. And then if I put a moon in front of the sun's surface, I don't get that background, I just see the emission from the corona very faintly. Okay. I'll just do it twice. Okay. All right, voting time. So a star's color reveals its surface temperature. What color is this star? Is it red, blue, green, or yellow? It's a 3,000 Kelvin star. This is its spectrum. It's a little blocky. All right. Is it red, blue, green, or yellow? Voting 1, voting 2, voting 3. I have majority red. Yeah, lots of red here. The other colors are. All right. This is a 10,000 Kelvin star. What color is this star? Red, blue, green, or yellow? I'm not sure if those are the colors of the voting cards. I should check. Nope, they are not. Okay, voting in 1, 2, 3. I should adjust that because asking people to vote blue and it's red on the thing is just cognitive dissonance, I think. All right. Okay, so what is this one? Red, blue, green, or yellow? Voting 1, voting 2, voting 3. Yeah, this is green. It peaks in the green, except that's our sun spectrum. The sun's not green. Our eyes have adapted to basically seeing the sun's light as almost white, maybe a little yellowish, and that's how we weigh it, right? So that's how we perceive it, but it peaks in the green. This is also why plants are green, absorb as much sunlight as possible. Yes?
Is that why when kind of have a pretty bright light, you close your eyes, it'll be a little bit green?
Yeah. So you have a little laughter. Yeah. Don't do that too much. So when you look at a bright light and you close your eyes and you can still see the bright light. That's literally your retina saying, that was too much. And the funny thing is that digital cameras can do the same thing, and it's a very weird thing to fix. Sorry, sidebar. Digital cameras do the same thing. So if you took a picture of something bright, with, for instance, the Hubble Space Telescope, they already don't like you doing it because they might end up, blinking away, and so you actually end up blinking away the bright source. And then then the next program comes along, and we take a new picture. You go like, oh, there's a little faint outline of a really bright thing in my picture. And so you have to wait for it to go away. So digital cameras do the same thing. And yes, there's a very friendly request not to look at something too bright, just in case we end up, blinking that away for the rest of the year. And so, first, the Harvard spectral classification. You go like, okay, Harvard, why is Harvard in there? It was because that's where the glass plates from all the observatories went, and the Harvard computers, the women who were comparing those were sitting in a room and comparing all those, measuring all the brightness of those stars. They did that. Here's the photographic plate. Like I say plate, and you go like, what is a photographic plate? None of you even remember film, I think. You may have one artsy cousin that does film, but nobody does film anymore, right? Little rolls of film, maybe. Granddad had those, yeah, okay. So that was already a step up from what we did before, which was a glass plate this big, and stick it in a telescope. It was like, had emulsion on it, so basically something that was smeared on it that was light sensitive and super toxic, so, you know, awesome. And then, you know, slide it into the telescope, expose it, come out, and then develop it with other chemicals. So those things were run on the telescopes during the night, and then the glass plates were carefully shipped to Harvard for looking how bright these things were. So they did that visually by eye, and they started noticing that there was a sort of an organization of colors. And so this became and so they also took spectra using photographic plates, and they ended up with these O through M classification of the stars, not just on where they were brightest, but also how prominent some of those absorption lines were. So you can sort of see that, you know, O star is a little bit here, and then it becomes more prominent, and then less prominent, not so much here. M stars have that. This one is really, really prominent, and they're, you know, redder. So there was a combination of how much absorption features do I see, and how bright, how hot these things are. You go, well, this is not how you spell in the alphabet. That was because it was they started with an initial classification, which had alphabetic organization, and then went, nope, that's the wrong way around, and reorganized it. So we end up with O, B, A, F, G, K, M, which is really hard to remember, but it is something that we just are now stuck with. So I'll have a mnemonic in a minute, and an opportunity for extra credit. So where's our sun sitting? So our sun is a G2. So not only did they have these letter types, but they started subdividing them basically on how strong the various lines were. So our sun is a G2 star, and you can really see that some of these have lots of features, and like the O star, for example, doesn't have a lot. It just has a bit of hydrogen there. And so mnemonic. So this was done by Cecilia Payne. And she realized that, yeah, we need to reorganize this because that's how they actually fit together. That's how we get from bright to, from blue to red, and the absorption features fixed that way. So this was her mnemonic, OBA, fine girl guy, kiss me. And I would like a different one. So if you can come up with a better one, I'm all ears. Or basically you can send it to my email. Because, for two reasons. One, I would like a slightly less creepy mnemonic. That's just, yeah. I was taught this, everybody's been taught this because that was the original one. But I'm absolutely happy to get a new one. And we have 3 more versions. So that's only the classification that Cecilia Payne came up with was based on optical, like what we can see, the light we can see. But there's also light you can feel, infrared. Bless you. And so in the infrared, we found 3 more categories of stars, the L, T, and Y dwarfs. These we know of as of 2011. So pretty darn recent. So there are smaller and cooler stars even than the M dwarfs. And so OBA, fine girl, kiss me, LTY is not a good mnemonic anymore. So I would love to hear one if you are good with words or making one. Okay, so these extra classes were called as the brown dwarfs, and they really they're sort of failed stars, but they are putting out heat, and they are really small. So this is the main star, and then there's a little dot next to it. So in 1995, that was the T dwarfs, L dwarfs that was found. And so we've been adding new classes ever since. Here's the funny part. It also meant that we found stars closer by. They're faint, you only see them in the infrared, so only in the heat signatures. And so Bernard's star discovered in 1916, and then Proxima Centauri 1917. So you go like Alpha Centauri was 1839. Okay, that's 19th century. It's like that was the closest. That's the first time they got parallax, and so they realized that that actually has a companion, and that's 4 light years away. But then in the quite close by, we find 2 more, and 2013, 2014. This is a decade ago that we've known about things. So, yeah, sometimes you find something new right in your backyard. Often you hear about Hubble has found latest and greatest thing extremely far away. And this is like, well, 6 light years is far away. That's right there. And we didn't know about it. So these are 2 stars that we're also going to look at, of course, with James Webb, because that's good with infrared and therefore heat, and see if there's anything, orbiting around there, because hey, that's pretty close by. So if we want to have the neighborhood of stars, so the ones that are actually physically close, rather than the ones that are in the constellations, we'll talk about those on Wednesday, because then Drew is here and he can show us constellations to color magnitude diagram. And so here we have Sol, Sun, and then you see all these different names like Ross 154. These are people that looked at every star and tried to figure out how far away they were, so they could actually see if it was close by or not. So Proxima Centauri, and then you see these occasional odd names. That's this Lauten, for example. That's a Dutch guy that was doing that. So these are the ones like where people find, this is a nearby star. So this is all within 15 light years. These are sort of the nearby stars to our sun. So this is the neighborhood. Let's see if I've got a fellow Trekkie in the room. Anybody recognize Wolf 359? They basically have this map sitting on their the writer's room and went like, what can be a fun sounding place to have, like, they're really close by to the Earth, right? So these are the nearby stars to our sun. So you can also see that there's like a 3-dimensional sort of graph to it, right? It's a blob of stars, these are the nearest ones. Okay? So we're still working on these searches, and so sometimes we can find them because, see that thing move a little bit? That's that parallax. See the little shift? Look how many weird wobbly dots there are, and then there's a dot here that moves a little bit between 2 years and so. There was a special telescope that actually did called WISE that is just shut down. It ran for a decade. It would scan the sky and it was looking for asteroids and these things. And so if you see something move, it has a fair bit of parallax, and then go, that must be something, because everything else sort of stays put. They're also these are the subtractions of brighter stars that they can move. So it's hard to find those cool fellas. So as we classify them, we go from O, B, A, fine, girl, kiss, me, L, T, Y. Again, nothing for this, so feel free to come up with a completely new mnemonic. So the O stars are 30,000 Kelvin and above. They are really bright. They peak in the ultraviolet, and we get from 10 to 33,000 Kelvin. That's B stars. A is 7,500 to 10. F, G. So here, this is where the sun sits in. And so you can see some of the examples of, Polaris or North Star is an F star. Arcturus is also pretty well known. Proxima Centauri, the nearest one, is already an M star. And then we have these smaller ones. Note that these are 700 to 1300 Kelvin or below 700 Kelvin. So you have to subtract like 250. 500 Kelvin it's like a really hot oven. It's not really that hot for a star, which is also why it only glows in the heat signature, right? You don't see, it doesn't emit a lot of light. And remember distances. So the next time somebody does this to you, you've got an answer. Just think, the light from that star was emitted thousands of years ago. It could be long gone. That's serious. It's 8 light years away. Just think, the light from that star was emitted in the previous presidential administration. Wasn't quite the same punch, right? It's like the kind of thing where it's like, well, oh, that was after Friends ended, or whatever the season is that, you know, this is not particularly, if we can see the star, if we can see the star, it's not that long ago. We're seeing it as it was a couple of years ago, maybe a decade or something, not thousands or millions of years. We see the far side of our Milky Way, for example, yes, then we're talking, well, that looks like it was when the dinosaurs were, or, you know, the dinosaurs died out or something like that. Well, that was 100,000 years ago. Oh, when our species just came out of the savannah. So we have all these terms for, and some of them are a little fanciful. So we have yellow dwarf, warm, stable, slowly growing. Red giant, that's something that we get into. Red dwarfs, blue giants. But then there's a bunch that we totally made up here. Most of them are either a combination of red and blue and giant or dwarf. Okay, so we do have something called a white dwarf, and we'll talk about why they are there, especially about stellar death. So how many different kinds of stars are there? So if you want to know, like, how does this all relate to each other, we find a big clump of stars that sort of look like they started off at the same time. We find a big ball of stars, and we're like, all right, they look like they appeared at the same time. We call those globular clusters. We had one in the very first group question that I asked you to. And so the assumption is they're all roughly at the same distance, and they're all roughly the same age. And then see how many bright ones there are, and see how many blue ones there are, how many red ones, and like see how that all compares. Yes? Is it a little too dim on here, or is it just too Monday? It's a little like, I can see some people just going like, this is such a comfortable state. It's fine. All right, so first things we're going to do, this is why I made it a little dark. We're going to zoom in on one of those. This is Centaur, totally a man-horse thing. And zoom into that. And here's one of those blobs nearby our Milky Way full of stars, right? So it's very highly calculated. And as we zoom in, we sort of switch telescopes, and at some point, so you can see how, you know, crowded a field that is, right? It's full of stars, and we're sort of assuming that they're all at the same distance. Now, we're zooming in somewhat further. I think this is one of the last pictures we used. And so you take a central chunk of that and you look at that with the Hubble Space Telescope. Hubble is great at seeing detail, but the camera isn't very good at it. It's not a pano camera. It is very much a zoom lens. Think sport lens plus, right? So we look at a tiny area with Hubble, so we kind of have to know what we're looking for and where we're looking. So as we zoom in the center, you know, you swap out telescope and go, now I can see more detail. You go for bigger and bigger telescopes. When we talk about telescopes, really the only thing is that you want to have that resolution. And so you can already say like, yeah, there's red ones and there's blue ones, there's all kinds. And so we now are at the Hubble picture of this where we actually resolve and also see the fainter stuff. There's lots of red ones, there's blue ones, and as far as I can tell, oodles and oodles of yellow ones. These seem to be the most common. These globular clusters are, if you look at them with another telescope, the whole thing looks pretty yellow, and that's because it's filled with these little yellow stars. Okay, so everything moves around in one of these, so we just take a snapshot. And so this is one giant blob of stars that are all orbiting each other. Yes, okay. So here's the picture. This is the Omega Sen. That's one of those globular clusters. We're going to make the HR, the Hubble Hertzsprung-Russell, or the color magnitude diagram, the one that we had when we talked about temperature and the cool and hot and bright. So if we now organize all the red ones, so we're going to zoom in a little bit on this, and then organize the red ones to one side and the blue ones to the other side. We'll move the red ones to the right and the blue ones to the left, and this is how we end up with the temperature going the other way. So we're organizing that first, so all the blue ones go on the left, so this is what you do when you don't know what's happening just yet. You go like, okay, well here's all the blue ones, there's all the red ones, oodles of yellow ones in the middle, and now I'm organizing everything that's bright at the top and everything that's dim at the bottom. okay, that is no longer random, right? So this is the main sequence of stars, and then there's a turn off in there, and here's the red giants. These are the bright red things. And then we've got horizontal blue, or basically blue giants. And then all the way down here that you can't see because they're idly piddly white dwarfs, but they are there. And so if you have a mix of stars that all appeared at the same time, then you can say, okay, this must have been, this is a population of stars that's X billions of years old, and they are made, and they have a certain distribution of yellow and red and blue, but most importantly, color and brightness for most of them are on the main sequence. There's a clear relation between those two. So we call that the Hertzsprung-Russell after the two folks that came up with it, or the color magnitude. So we have color here on the bottom, or we say like, yeah, that's temperature. So it's a color magnitude diagram. I may slip up and call it that as well. So it's either Hertzsprung-Russell or color magnitude. These things change. These things are named interchangeably. And so there is this main sequence of stars where we start faint and red, go to brighter and yellow, and end up in blue and really bright. Yeah, so we crank up the temperature and we get brighter, and then there's a group over here that is just as red as these dwarfs, but they're much, much bigger. And those are called the giants, the bright giants, the supergiants. These are the absolutely massive stars that we can find. And there's a group down here called the white dwarfs, which are just as blue as these bright blue ones here, but they're all the way down there. They must be really, really small. So you can learn a few things already, like you get their temperature, and because of their relative brightness, you go like, okay, these must be small, these things must be big, these are cool and big, these are hot and big, these are hot and small, these are cool and small. Yeah? Okay, so we learn a lot from just looking at the Hertzsprung-Russell graph. And also, where do most of them sit? Most of the stars sit in the main sequence. And that was just called, oh, that's the main sequence, and that name stuck. So we call that the main sequence. And then we have these newly discovered ones. They're actually just an extension here at the bottom, like basically dimmer and dimmer and redder and redder. So we have O stars, B stars, A stars, F stars, G-type stars, K-type stars, and N-type stars, right? They're all along this main sequence, but there is also N stars up here and B stars down here, because they have the same temperature. So they look similar in temperature, but these are the massive ones, right? These are the giants. So there's lots of stars which have a luminosity which places them above the main sequence with the same temperature. These are the giants. For example, the funnest star to say 3 times Betelgeuse. So, Betelgeuse you may have heard of because it is in the top in Orion, and I don't know, about a year ago there was this whole thing about like, yeah, it's dimming. Oh boy, could something be happening? And like most of the time when something's dimming, it just means that an interstellar cloud moves in front of it. But the hope was, it could go supernova. That'd be really fascinating. It wouldn't be great for the human race, but it would be really fun to watch because we learned so much about supernova. So it's supposed to go supernova soon. And this is the part where stellar astrophysicists have a very different definition of the word soon than the rest of us. Because we go like, oh, soon, so next Friday? And they go like, oh yeah, in the next 100,000 to 1 million years. Okay, I'll clear my schedule. So what do those big stars, how big are those supergiants, right? So Earth, we are here. Venus, the rest of the rocky planets, Neptune. You get an idea of like how big Saturn with the ring is. There's Earth. Jupiter is already a pretty big fella compared to the rest. And this is the sun, right? 98% of the solar system, our own star. That's not even Earth, that's Neptune now. That's Sirius A. This is Pollux. It's an orange giant. That's our sun, by the way. That itty bitty orange thing over there. Keep track of where it is. Arcturus is a red giant. Aldebaran, another fantastic, also Star Wars name. Rigel, the Pistol Star, is a blue hypergiant. Antares A. Yeah, our sun is a dot over there, maybe? Mu Cephid. And this is the largest VY Canis Majoris. Canis, the major dog. Yes, the surface of that thing would look flat if you'd be right above it. So the size of our Earth, this is the supergiants. These supergiants is not a misnomer. They are extremely large, right? So some of those are big and hot, as you saw. They were bluish white, but the majority are red, right? The majority are sitting above the main sequence and well far away. I like this graphic because it really shows that, you go like, yeah, it's bigger. You're like, well, everything is just bigger. It's just a superlative, and that doesn't work in astronomy. So I'm like, yeah, this is how much bigger, way bigger. And then we have this other thing. It's not this one. It's this thing here. That's a white dwarf, right? This is a normal star. That's the white dwarf. So they're sitting over here. They're faint, but they're relatively hot. They're so hot that they're almost as hot as the B stars, for example. We're going to talk about those. So, for example, here's a cluster. We look at it in detail. And those little bitty dots, those are the white dwarfs. We'll talk about those when stars die. This is leftover stuff from when a star has actually completely exhausted its fuel and exploded. So, we don't see a lot of giants. Most of the stars are here in the main sequence. This is basically a relatively short-lived evolutionary stage. And so you move off the main sequence, live here for a bit, explode, and then end up here. Does everything end with an explosion? Yes. So, all the vast majority of them anyway do. And so these are sort of leftovers after the red giant, the giant phase. So, but to give you another graphic, because you can't see the visual on the PDF. This is Betelgeuse. This is like the orbit of Venus is well inside Betelgeuse. This is Aldebaran. This is the sun. And then, for example, the white dwarf is 1/100th of a solar radius, so it is literally 1/100th of our own. It's the size of the Earth. It is just a little cinder left over from when a star died. Okay, so we're going to talk over all the things. There's one thing that I need to talk before we talk about this. So I said most of the stars live on the main sequence. This is a actually observed part, right? And as they move off, the first ones that move off are the hottest and biggest. And let's see if I can get. I thought I had a little video of that. Where's my video? Nope, that's not the video. Okay, it's in the next one. So there is a relationship between the mass for the main sequence. So if you're on the main sequence, if you're down here, you're dim. If you're up there, you're bright. With me on that? Okay. Small, dim, cool, hot, big, and massive. Right? This is one solar mass. The sun sits here. This is 60 solar masses. You have something 60 times the size of the sun. Much more massive. So the more along the main sequence I go, the more massive these stars are. However, here's the flip side. Stars also, over here, burn a lot more. They go through their fuel much, much faster. Think of it as it has a bigger fuel tank, but it also has a lead foot, right? It's going through its fuel as fast as it can. So weirdly, lifetime is the other way around. So if you go for a lifetime, is the total fuel available by the rate of fuel consumption. So the mass divided by the luminosity, because basically as fast as I burn that, I'm radiating that out. So if I want to calculate that, this goes as the mass to the fourth, and this is going to 1 times the mass. So it's basically basically the time goes as 1 over the mass cubed. So the bigger the guy, the faster they burn. So, so you can literally go like, you express this in solar masses. So the sun, 1 cubed, that's easy, 1. And so that's 10 billion years. But if I go with 60 cubed is, I don't know, 1,000. That's the nearest ballpark. This is how astronomers do math. I'm close enough. So then I end up with a thousandth of 10 billion years. Well, that happens to be about 1 million years. So those the brighter main sequence stars live much, much shorter. So lifetime goes the other way. This is sort of the tortoise and the hare. Everybody had that in school. Yes, the tortoise and the hare. This is the hare. Live fast, die young, and leave a smoldering corpse. This is the tortoise, right? It just burns it slowly. The lifetime of 0.2 cubes is something like 0.001, I think. 0.001. Put that in here. Something down here, or even lower, can live for 1 trillion years. Our entire universe has been around for about 13 billion years. So yes, the M dwarfs on this side, you go like, oh, has any of them evolved off the main sequence? Has any of them died yet? Like, well, we're going to have to wait, I don't know, another 10 times of the universe before these things actually start switching off. They have a small fuel tank, but they're burning it very, very slow. See the analogy? Prius, leaky, farty car, right? It's basically brand new. So these burn through very, very quickly. We can learn another thing. The short lifetime means that if I see these, they formed in the last 1 million years. 1 million years isn't that much. I mean, in geological terms, if you talk to a geologist, they go like 1 million years, yeah, we can barely tell the difference between 1 or 2 million years ago. It's like it's a little thin layer. So if you see them, they must have just formed, because if as soon as we stare at it for a little longer, not as humans, but proverbially, in the lifetime of stars, these things live in a flash. They're and gone. So these move off, become red giants, and then die first. And so you go down this list. So if you still see those, the whole group of stars just formed. If you still see these, then it's 7. That's 17 and a half. Here we go. So if I see these, the whole thing has to be at least 100, like at maximum 100,000 years old. If I still see these, then it's at least 1 billion years old. If you see the sun or its brethren, then the whole thing is at least 10 billion years old. So they're still around. But if I don't see those anymore, I know that that it's aged. Does this make sense? I need to find the video real quick, because then you see them move off real fast. So live fast, die young, leave a smoldering corpse. And so when this turns off, so here's the main sequence, and where the main sequence stops tells you how old the whole thing is. Where you see these things move off to the main sequence, like whoop, they go off to the red giant branch, like they have stopped their life on the main sequence, so they've burned through their initial fuel. Okay, so that's the main. We can talk about that later. I want to do the group work. So if you look at a group of stars, so look at our Hertzsprung-Russell diagram, and there's just a couple of questions here. And then you can see you can rank them where they turned off first. So by just looking at color and a whole bunch of stars, we learned a whole bunch of things in one go. And then looking at a bunch of groups of stars, we realized that they sort of come in a sequence of ages. And so that's where the HR diagram really became handy, because we could start figuring out like, hey, how long does this is where these lifetimes come from, right? This is figuring out how long these groups of stars live. Okay. While I still have you all, if you can't make the midterm date, let me know, because there's always a couple of people that are on tour or something. We can schedule an alternate date. So if you have an issue on Wednesday, please let me know. Then we can do it. There's lots of Athens that can never make it, so it's fine. So, moving off the main sequence is a sort of not slow, but a few thousand years, and then move into this red giant. And so they become this red giant, and this is when they burn their sort of they get a second wind. So they start burning instead of hydrogen, they start burning helium. But there's not as much helium as to begin with, so and you don't get as much energy. We'll talk about that on Wednesday. But sort of you go like switching to auxiliary fuel, right? And so you go on a little further, but then the whole thing implodes, and we start talking. Next week we start talking about how we start end. They explode in spectacular fashion, and the bigger they go, the harder they go. It is supernova are a thing, and they're quite fun to watch, but preferably over a galaxy, literally, or the far side of our one goes off near us, then might get fried. Yes, this is an unpleasant thought, but yes. Not that anything is going to explode into us. Yes. Okay. So we're a rank these, right? So I'll put them on. Okay. I'm gonna, you were like, okay, I'm done. I don't know. So, temperature, blue on this side, red on that side. Yeah? Okay, which one of these has most of its main sequence? A, B, C, or D? Which one of these four has most of its main sequence? C, right? C. This one's, they all arrived, they just got ready, they're on the main sequence. The first one here at the top started to turn on. So this is what, a million years the O star has given up and is becoming a red giant. So this one so far is our candidate for the youngest. Which one has the least of the main sequence? B, right? So this one's the old, this is definitely the oldest, right? And so, okay, this one, then this one, then this one. What's happening with this guy? Okay, you kind of go like, this one already had 1, 2, 3, 4, 3 of them turn off. Here, 2 of them turn off, like they're even further. These guys haven't even cooled down onto the main sequence yet. So when the whole thing forms and we're seeing star forming regions, we see big clouds of dusty stars forming brand new stars. This is fascinating to watch because we're also looking for the planets around them. These are the ones that first sort of reveal themselves, they blow away their cocoon, and so you can see them.
these are idly piddly. It takes them a while to blow away their, dust shroud around them. So you see them a little brighter because it's also the cloud and gas around them. They're sort of like the not so great chick that's still trying to get out of the egg. That's these guys. So this one's even before C, like it hasn't even gotten everybody corralled onto the main sequence just yet. But I didn't talk about that. I wanted you to reason just with the top of the main sequence. This is the youngest, then this one, then that one, then that one. See my logic there? Like how much of the... Well, I'm glad I was fast talker there. So, okay. Not sure what my laptop is. Oh, yeah, so I plugged it in, but the plug went nowhere, so that's why. Okay, I'm glad I talked in just exactly 50 minutes. I don't know about that right now. All right. Thank you all. We'll continue this on Wednesday when I actually try to animate the Earth diagram as well. Leave it on the technical station.